Good day. Welcome to my talk on spectral small-gain theorems for input-to-state stability of infinite networks. My name is Mironchenko, and this is a joint work with Christoph Kavan, Abdallah Sviker, Navid Norozi, and Majid Zamani. We live in the world of networks. We are surrounded by transportation networks, electrical grids, social networks, which grow larger and larger from year to year. Emerging technologies like 5G, Internet of Things, cloud computing make this trend even more distinct. Safety and reliability of these networks need to be analytically verified. At the same time, the existing tools do not scale to today's increasingly complex systems. This is in particular due to the fact that for most designs, the size of the system has to be known in advance. At the same time, for many applications, the size of the network is unknown or even may be time varying due to the agents which enter or leave the network. One of the ways how one can counteract to this challenge is to over-approximate finite but large network of unknown size by an infinite network, which captures the essence of the original interconnection. Today, we would like to study one of important problems arising on this way. Under which conditions an infinite interconnection of stable systems is stable? Small-gain theorems are a powerful tool to analyze such a problem, especially in case of nonlinear subsystems. At the same time, most small-gain designs are limited to finite networks. Today, we present Lyapunov-based small-gain theorem for infinite networks. We study an interconnection of countably many systems such that each subsystem is given by an ordinary differential equation. xi is the state of sigma I, xi bar is the vector of the states of neighboring subsystems, and this is an internal input to the system sigma I, and ui is the vector of external inputs. We assume that fi is a continuous function and that the solutions to the system exist and are unique for each initial condition and all inputs. We would like to rewrite these equations in a vector form. To this end, we collect all the states xi, inputs ui, and right-hand sides into the vectors x, u, and f. Then the network takes form of an infinite ordinary differential equation. However, these equations of motion do not fully define the network because we need to specify the state and input spaces for this system. To this end, for each finite p, consider the Banach space LP consisting of sequences which have finite LP norm, where LP norm is defined in this way. Now we are able to fully describe our control system. So the network is given by these equations of motion, which are infinite dimensional ODEs. The state space we consider as an LP space for a finite p. The space of input values is denoted by U and is given by LQ for a fixed finite Q. And the space of input functions is the space of measurable and essentially bounded functions which map R plus to U. Having fully defined the network, we proceed to its stability analysis. We say that the system is exponentially input-to-state stable if it is forward complete and the trajectory satisfies such an estimate, where A and M are positive reals and gamma is a class K function. That means that gamma is continuous, 0 at 0 and increasing. One can see that exponential ISS unifies two properties. One of them is exponential stability of undisturbed system, and another is input to output stability. Indeed, if we take the initial state equals to 0, then the trajectory is upper bounded just by the function of the norm of the input. This feature that ISS unifies the stability of the undisturbed system plus the input-output stability with respect to external inputs has made ISS one of the pillars on which the modern nonlinear control stays. In fact, ISS is a dominating paradigm behind robust control and observation of nonlinear systems, and behind analysis and control of large-scale networks. ISS was introduced by Eduardo Zontag in 1989 for ODE systems, but only in the last 5 or 6 years it is being actively developed for infinite dimensional systems. For the survey of the state of the art in this theory, we refer to this paper by Eduardo Zontag, which contains the results for ordinary differential equations, and to this recent paper collecting the results in infinite dimensional setting. Having defined the stability notion, we need the tools which help us to analyze these properties. We will say that a continuance function V is a EISS Lyapunov function if it satisfies such sandwich estimates for all states, and that the derivative of V along the trajectory for any state and any U satisfies such a dissipative inequality. Here kappa is a positive number. In particular, if U is identically 0, then this term vanishes and the trajectory decays exponentially to 0. If U is present, then the trajectory decays as long as x is large enough with respect to U. One can show that existence of such an ISS Lyapunov function implies exponential ISS for the control system. Now we can proceed to the main question, that is, under which conditions an infinite interconnection of exponentially ISS systems is exponentially ISS. Our main assumption is that all subsystems are exponentially ISS and have exponential ISS Lyapunov functions Vi. Vi satisfies such sandwich estimates and the dissipation inequalities of this form. As each subsystem has external inputs and inputs from other subsystems, we have a number of parameters describing the interconnection. These are external gains, which we assume to be uniformly bounded, and internal gains, gamma ij, describing the influence of the system sigma j over the system sigma I. We also assume that the decay rates cannot be arbitrarily small, which is a necessary assumption to be able to get some kind of stability for the interconnection. Also, we assume that these sandwich constants also can be chosen uniform in I. We would like to rewrite the dissipative inequalities in a better form. To this end, we define the operator lambda, which is a diagonal operator collecting all the decay rates of subsystems. All the internal gains we collect into infinite matrix gamma. And now we can define the gain operator, which we understand as an operator mapping L1 to L1, which is defined by this formula. We also introduced the notation for a vector of Lyapunov functions of subsystems, as here. With this notation, the dissipation inequalities take the following form. So, as we will see, the crucial knowledge which helps us to show the stability of the interconnection are the properties of this operator. So, however, now we see that this operator is also very important because it describes, in a certain sense, the decay of this vector Lyapunov function. Our next aim is to relate the properties of the gain operator psi with this operator. To this end, we also assume that gamma induces a bounded linear operator on L1. So now, assume that the spectral radius of the gain operator is less than 1. Assume also that the decay rates are bounded. Then there is a vector mu, so infinite vector, which is uniformly bounded from below and above by positive constants, such that mu is a left sub-eigenvector of this operator. So, nice properties of the gain operator imply nice properties of this operator. This will be extremely helpful for our main result, which is small gain theorem for infinite networks. Consider the network sigma with fixed P and Q. Assume that all subsystems are exponentially ISS with corresponding exponentially ISS Lyapunov functions. And assume that the corresponding dissipativity and uniformity conditions are satisfied. Assume that the small gain condition holds. Then the whole network is exponentially ISS and admits a continuous exponential ISS Lyapunov function V, which is a weighted sum of Lyapunov functions for subsystems. And the weighting coefficients are given by this vector mu, which we obtained from the previous lemma, and for which this condition that the spectral radius of the gain operator is less than 1 is crucial. Also, we can obtain the sandwich bounds for the function V, and we know that V satisfies such a dissipative inequality. And we can even estimate this decay rate of the Lyapunov function for the network. Our results generalize the exponential ISS small gain theorem for finite networks, which was shown in this paper. However, this generalization is far from being straightforward. The results in this paper use Perron-Frobenius theorem. There is an infinite dimensional generalization of this result, which is called Crane-Rootman theorem. However, the assumptions of this theorem require at least quasi-compactness of the gain operator, which is a too restrictive assumption for applications. We instead developed another approach which does not require the compactness of the gain operator, and so we allow for general bounded operators. Moreover, our small gain condition is tight even for finite networks with linear subsystems, and thus our small gain result cannot be improved and is basically a final result for the networks with linear gains. The detailed proofs and discussion of this result is given in this paper, which is submitted to IEEE 10. Now I would like to give a simple example. Assume that we have an infinite network of linear systems of this form and each BII is positive. So it is easy to see that each subsystem is exponentially ISS. We assume that X is L2, and it is easy to see that this can be chosen as ISS Lyapunov functions for subsystems. We easily verify the dissipative estimates and obtain the decay rates and internal gains for subsystems. We collect all these gains and we can define the gain operator psi, which has a particularly simple form. So only two diagonals are non-zero, otherwise all the coefficients are 0. If the spectral radius of this operator is less than 1, then the interconnection is exponentially ISS. This is one very simple example, and we have other examples also for nonlinear systems in the paper. More importantly, the small gain theorem which we have presented can be generalized to exponential ISS with respect to closed sets. And in this form, it allows to study also stability of infinite networks of time-varying systems, the consensus in infinite agent systems, and the design of distributed observers for infinite networks. We have studied these problems in this paper. Also, I would like to mention that there are several further small gain results for infinite networks with nonlinear gains. Overall, we have developed exponential ISS small gain theorems for infinite networks, which are based on the spectral small gain condition. These results do not only give sufficient conditions for stability of the network, but show us that a Lyapunov function for the overall network can be constructed as a weighted sum of Lyapunov functions for its subsystems. Our results are tight, cannot be improved, and fully generalize the corresponding results for finite networks with linear gains. Our results can be also extended to handle ISS with respect to closed sets for infinite networks. In this form, they can be used for analysis of time-varying infinite networks, for consensus in infinite agent systems, and for the design of distributed observers for infinite networks. At this point, I would like to thank you for your attention, and your questions are warmly welcome.